Hello everyone, welcome to day 2 of our Open Source event here in Zug. Today we start with the open hardware topic. Happy to have Daniel here. The stage is yours, Daniel Bowie.
Thanks for the introduction. So, hi everyone. Maybe let's start with a small prologue before we kick off the presentation. So first of all, I think this conference is amazing because the audience is optimal for the kind of talk I want to give today, because I do not really need to debate to you that open source, and more specifically open source software, is amazing and we should all do more of it. Second of all, the conference is amazing because it is actually called open source at Siemens and not open source software at Siemens, because open source is certainly more than just software. And maybe some of you think that open source hardware, here specifically, is like the ugly small little brother of open source software, but I want to argue today that this is actually quite mature already, and you are already impacted every day when I was at a little bit. So just a brief example, when I prepared for this talk, I looked at some of the talks from last year's conference, and there I stumbled over a talk from Cedric Homburger, who introduced MTDA. So you do not need to know what MTDA is. The only thing you need to know is that MTDA is a piece of open source software which, combined with this particular piece of hardware, becomes much more powerful. As a matter of fact, you use this kind of hardware and you can suddenly do something with the open source software which you could not do before. You can interact with embedded systems much more easily. So open source hardware is already actually a done deal, and if you know it or not, it impacts all our life every day. So, with that said, we would come to the core of today's talk, which is not actually open source hardware, but these small little black thingies you just saw on the PCB itself, which is the integrated circuits. So we might be able to take open source software and run it on these small little chips, and we might have open source hardware to specify what these ICs can do and where to position them on a PCB. But what we do not have today is that we have a full insight what is happening inside of these chips. And this is actually a problem if you want to use it to their full extent. And even worse, we cannot recreate these chips. If the vendor goes out of end of life, the company, we do not have any way to recreate the chips again. And with that said, I would have today the hypothesis that semiconductors is actually the final frontier of open source. So it's essentially the last thing which stands between us today and a future where we are in full control actually of our computing hardware. So, with that said, I'm Daniel Bovensieben. I'm doing normally research on industrial communication. This is very important to mention because I'm no professional when it comes to semiconductors, so this is just some private hobby thing I do outside of Siemens. At Siemens, people still laugh about this topic, but I hope maybe I can convince some of the people that this is actually important. And as mentioned, I'm located in Beijing, China. So, I learned from yesterday's talk that good engaging presentation starts with some thought-provoking questions. So maybe if you're already awake, maybe some of you can raise their hand if you would say yes to one of the following questions. So first of all, does anyone have at least a basic knowledge how you would design an application-specific integrated circuit? That's great. So now to check the Dunning-Kruger effect, so it's not that many. The second question, would you know or would you think that we could actually do this manufacturing process open source? It depends. Very good point. And then the last question, would you actually dare to design one by yourself? So there are two people. That's actually better than I thought. So then let's maybe get started. So let's have a brief look on an ASIC design flow. So I simplify it today quite a lot, but nevertheless. So everything usually starts with that we have to define somehow how an ASIC looks like. So usually you have something called a hardware description language. In the industry, that's usually Verilog or VHDL. That looks something like that. Do not be in any way confused. This has nothing to do with a regular programming language where you think about maybe time and flow from A to B, but you more think about area, how you define something. Out of that, we usually then have some kind of synthesization process where we then create small little hardware components which we can actually manufacture to match this kind of hardware description. Then with another magical process, we come to the photomasks where we actually have it really lay out and to create these components in something what can be really manufactured. And then with a lot of expensive machines, we have these small little ASICs in the end. So we essentially create the photomask, and then the lithography machines work on this ones to expose on the wafers. So today, I won't go into the last point. So there's a lot of discussion these days that everybody wants to build their own manufacturing facilities. I would not recommend that. So if you do not want to live next to BASF, you also do not want to live next to a semiconductor factory. It's not a great kind of clean industry. But today we talk about the part from HDL to how to get the photomask, and the question, can we actually make that open source? So one important thing what we need is nevertheless the fab, so the fabrication unit, which has these expensive machines and can tape out our chip. And we start with the design. So usually the design looks like the HDL I just showed you, but sometimes you actually separate between soft design, soft cores in this HDL, but there's also something called hard cores where you actually need some input of the fab, so-called PDKs or process development kits, which you get from the factory. And they contain a lot of information, what can be manufactured, and maybe some kind of standard cells. And with these ones, you can actually create also designs which are very optimized. So moving on, then there's the synthesization process where you cut down your HDL to something what actually could be logically manufactured. We will look at that one in a moment. And I want to make a brief cut off here. We talk about FPGAs. This is not really relevant for today, but it makes sense in a moment. Why do I mention it nevertheless? So you just need to be aware that after the design to the synthesization process, you could actually put your design also in a field programmable gate array. I will mention a little bit later why do I said that. So, but let's go back to the ASIC process. So again, you need some input from the fab, and you will notice that more and more that we all the time need something from the fab. So again, this PDK, the information, what kind of cells they provide, for example, an end gate, how does that is being manufactured by this particular factory. You need that to then cut down your design. Then we go to the floor and power planning. So we have a certain size which we can manufacture, and then we say, okay, here I put certain functional blocks, and this is how I connect, for example, to the power, but also how do I connect the functional blocks to each other. We will also have some example later. Again, we need some information from the PDK, from the vendors, to actually have an understanding how large the production process will be, so to make these size estimations. Then we go into a little bit more detail. We really place then these cells, these, for example, AND or OR gates on a simplified manner. This will result in filling these predefined blocks. And then we also route between them, which is also a process which needs input from the PDKs again, because we need to know where does the manufacturer put actually these kind of interconnections on the chip. And then something in the software industry we are usually skip. Is all the intensive testing, but in this hardware industry, that's actually an important thing because now the process, taping out the chip, takes months. It's very expensive, so you do not want to make any mistake you can avoid. There are things like static time measurements where you get a model again from the fab how their system behaves, how long it takes for signals to flow from A to B, but also you get some design rules, what can actually be manufactured realistically. So you can design one thing, but what can really be manufactured is a completely different thing. And then there's also a check back that what you have now generated over this long flow, is it actually still matching what you now wanted to plan in the very beginning? And then at the very end, we are at the file format, for example, GDS2, which defines the photomask, and which we can then really give to the fab. So, and then we are already done. If you are a little bit confused, so I'm certainly confused. So if you're not confused, then I'm impressed. That is really a convoluted process, and this is actually also one of the things now which I want to make clear. And this is already simplified. So there are steps I have skipped for clarity. So it is quite a mouthful to actually come from design to chip. So with that said, after we have built a stage, so at the moment, It's very common that there's a lot of different vendors, Siemens is one of them, who fills these small little squares with some kind of software, but also with some kind of IP and, of course, definitions. So now the question again, could we actually do that in open source, and what would it actually mean doing it in open source? To simplify now a little bit more, to design this application-specific integrated circuit, I would say there are three main components. We have this register transfer level, which is essentially the way you design these things. The HDL would be a good example. We have this electronic design automation tooling, which was this long flow from synthesization to generating the files for the photomask. And then we have the PDKs, which this process development kit, which we need from the factory to know how and what to manufacture in the end. So when we now cut it into these three parts, maybe let's have a look individually if we can do that with open source. So let's start with the register transfer level for the design. So as I mentioned before, Verilog and VHDL, hardware description language-wise, is more or less the industrial standard. Verilog in the open source environment is much more popular than VHDL, or I think it's actually mostly used. I think VHDL in the open source environment is very limitedly supported for the reason I come to later. But as you know, if the open source community jumps on something, then they usually first build more tooling, but then forget to do actually the rest. And something similar happened here also with the open source semiconductor movement, that a lot of people created a lot of languages now. There are things which are Scala-inspired, like Spinner HDL, Chisel. BlueSpec is an interesting previous proprietary language, now open source language, which is used by Oxide Compute to actually design part of their compute hardware. And Amaranth HDL is, I think, worth mentioned. It's pretty new, but has quite some following. So then we have intellectual property. So one of the important things about open is that these days you would go to a company who lives from designing certain kind of logics and sells that to you. So it's like a software library you would include. You would not write like a crypto library in software, and similarly you wouldn't probably build your own CPU. So you go to a vendor usually and acquire their intellectual property and integrate it into your system. It's actually a very common thing, and probably most ICs are actually accumulation of these kind of IP blocks. And we have open source for that too. So as a matter of fact, RISC-V is a big thing. So often when I talk with people about RISC-V, they always tell it's not really open because it only defines the ether. But as a matter of fact, having an open ether now enables you to really build open CPUs. And there's a bunch of them, and was mentioned is here the Pico RV32, which is a small CPU based on RISC-V, where you have the whole hardware definition available and can essentially synthesize that thing by yourself. Then you have things which are not really RTL, but I nevertheless want to mention it here too, which is Open RAM, which is actually more like a framework to generate RAM for you. So it doesn't give you a block of certain amount of RAM, but you define how much RAM do I need, what are my constraints, and then it will assign on your die a certain amount of space for that. And then you have things like FASOC from some universities which generate analog components, which are also quite important, for example, for power, but also for some kind of sensing like temperature. It's not really RTL, but nevertheless, I wanted to mention it here, So, and then last but not least, very important for open source is always the communities. And yes, there is already quite a big community around open source semiconductors. So we have this open course, which is already over 20 years old. There's, of course, also some forks. Nevertheless, I would like to mention Liberal Course from the Fuzzy Foundation, which is already closed down, but nevertheless, there were some activities. And in the end, at the moment, I would say everything strives in the end to GitHub. So you can just manage your designs also on GitHub, because in the end, it's also just some kind of definition in a file. So with that said, I think it's fair to say, yes, designs can be done open source, and we actually have quite a bunch of open source-based IP cores. Coming to EDAs. So I hope I cut time-wise a little bit down because it might get very complicated, but now I hope you can stick with me there. So all of the things I will mention are very important, and it's maybe a little bit unfair to single one thing out as the most important one, but I think USES is one of the things which actually made it possible to really think about this whole process to make it open source. So OSS is actually a tool developed by Claire originally for an open source FPGA flow, and they are coming back. Why did I draw it actually in here? So there the idea was, can I only with open source tools, without the proprietary stuff, come from a design to a bit stream which I can push to an FPGA? Several years ago, that was considered not possible at all. With OSS, it's not only possible today to make that to one FPGA, but to the whole huge family of FPGAs from different vendors. So, and the interesting thing now here is that even though that it was originally designed for FPGAs, it can also be used in this synthesization for ASICs. So OSS is a very important point to make that possible. And it's not a trivial task to do synthesis. Then we have an interesting project called Open Road, which is originated from DARPA. So DARPA has realized some years ago that design cost and design complexity goes higher and higher and higher. And they started funding this Open Road project, where the vision was to have an end-to-end, so an RTL to GDS design flow, where you essentially do not have any human anymore in the loop. So that comes with some caveats. So maybe some of you are confused, so why is there this whole compilation process similar to software, even a human in the loop, but you actually commonly need to interact with this flow to optimize specific things. So often it doesn't work, or you need to adapt to certain constraints, size, power-wise. So having the vision of having no human in the loop is actually a quite dramatic shift here. And Open Road tries to address that. That's also the logo essentially established the idea of having a turnaround from design to GDS in 24 hours. Then we have a lot of additional tooling. I won't go into the details, but just that you know, there's a lot of stuff available to then test your designs and prepare them for production. So again, also from Open Road, you have OpenStar, which does the static timing analysis. K-Layout is a pretty old tool, which does design rule checking, and the layout versus schematic you can do with NetGen. And then last but not least, we have Magic, which is a probably even older tool than me, which generates the GDS in the end. Then we are through. Again, very much simplified. It gets actually even more complicated because some of these tools are reused during the cycle. So for example, Magic can also do the design rule check, and K-Layout can also generate GDS, and that's actually done for certain reasons, which I don't want to go in. But I think the point I would like to make here is there is tooling available for all these steps, but it's still pretty convoluted. And now to innovate a little bit on that one, to have this end-to-end flow, there's a last tool I would like to introduce, which is called OpenLane. So OpenLane is now this implementation of the vision that we take all these tools and put some glue logic in between and have this end-to-end flow. So essentially it uses all the tools I just mentioned, the things from Open Road, from OSS, Magic, NetGen, does a lot of additional things, also provides some interaction with this flow that you can optimize it, and then you can essentially come from RTL to GDS by just calling essentially one program, and saying it simply. So, coming to the last and actually most critical part, which is the PDK. So I think it's fair to say the design and EDA is a done deal. There maybe lacks some maturity, but nevertheless we can make a check mark on that one. But the last thing which always stands in the way of an open semiconductor was the PDKs. And I will explain in a moment why this is. So just a little bit historically from the process nodes, so from the sizes, how can I produce a chip? So from the 60s to the 20s, you can see there is some progress. And now just zooming in on the last 20 years, there's still some progress happening. So this is not completely at the end of what is possible, even if we come close. All these individual dots here represent certain generations of process nodes. And this process nodes means essentially how small can I produce. In the past, this particular number really means a physical property. These days, it's more like marketing. The claim I want to make here is that for every dot, there are certain end companies who have a certain PDK, which is usually not open. So you actually need to go to these vendors, and if they talk to you at all, so usually they wouldn't talk to people like us because we are not really the kind of customers they think it's worth talking to. But even if they would talk to us, they would only give us the information about how to produce something under an NDA. And this is completely not acceptable and not open at all, because that means we cannot talk about the PDK, and even to a certain extent the designs we then create, we cannot share. And that is completely voiding the point of open source. So now you would think it's quite easy. There's so many and there's hard competition. So just one of these ones should be innovative enough to stand out and say, hey, I try something new. But actually that didn't happen until 2 years ago, or a little bit more than 2 years ago. So Skywater, which is maybe a company not all of you know, is a rather small fab, which actually released their PDK, the 130 nanometer process, as open source. And interestingly, after this was done, and I will mention in a moment why they actually did that, Global Foundries also came out with an open PDK, in this case the 180 nanometer. And currently, Skywater is actually working on a 90 nanometer open PDK. So what does that actually now mean that it's open? That means you can go to GitHub and you can download the specification, the standard cells, to really create something what could be produced by these ones. And to give you just an indication, what does that mean, 180 nanometer, 130 nanometer, because it's quite far in the past. Just to give you an indication what you could in theory be built on top of that one. So the Athlon, for example, was built on 180 nanometers, Pentium 4 on 130, and an AMD 64 Opteron on 90 nanometers. So of course be careful, not by these fabs, but the generation of the process node was the same. So with this now set, we have all these check marks now. So we have open designs, we have tooling, we can put it into a very neat flow, and we have now this open PDK. But can we really now do something with that? I mean, we can maybe play at home and visualize how a chip would look like. And the answer is actually yes, we can, and yes, we actually did. So actually, I also have today now one of the very first tape outs of a chip, which was really taped out from Skywater with this kind of flow. So this is not just an academic idea and an academic collection of tooling. What might be possible, this is possible, and we have done it. So now the big question, could you also do it? So I mean, you might think, yeah, okay, with a lot of time and a lot of money, you can do everything. But could you now also do it? And also to maybe say that for up, I think yes, and I also think you should. And for that, I actually would like to introduce 3 programs which are running these days. The first thing I would like to mention is the Open MPW. So MPW stands for Multi-Project Wafer, and is essentially illustrating the idea of taking one wafer and splitting the space you have there between different people so that they can actually, they have of course a smaller space, but at least they can share the cost for this particular wafer. And Open MPW is actually an initiative of 3 companies to make that wider available. So one company is called eFabless, who did these MPWs in the past, but they used a closed PDK, so it was not really open, but they at least tried to use the EDA tooling and also integrated some of the open RTL. Then the big breakthrough was that Skywater now opened their PDK and allowed eFabless to cooperate with them to then produce it also with an open PDK, and then allowed us to also talk about it. And then most importantly, and also the key why it is open, is Google, who actually opened their wallet quite widely and sponsored all of that. So I think it cannot be overstated how much of an impact Google had here. So they not only paid for the tape outs, they're also as a lead answer convinced Skywater to open their PDK, which they didn't do before. And they also sponsored a lot of individual contributors, universities, but also individual contributors to push their EDA tools and push the individual elements to come to a state where this can actually be done. So the specific details is that there are at the moment 8 shuttles, so that means 8 runs of different tape outs. Every shuttle has 40 designs, so 40 people can join and put a design on a real tape out and then receive these chips. The area you have is like 10 square millimeter, what maybe doesn't tell you a lot, but it is actually reasonable, and it will come in a moment what you could actually do on something like that and what people have done that. And the only and one caveat of all of that one, because it's for free, so the 40 people or the 40 entities who participate do not need to pay anything, but the only caveat is that everything needs to be open source. You can only participate if your whole design is being as open source released. And that's the caveat for us. It's so I think that the setup is great. The only problem here is that 40 designs turns out to be very little. So actually, when this was announced, very quickly more than 40 people on this planet actually said, I can produce a chip for free. Yeah, sure. So there's more than 40 people on this planet who would like to do that. Maybe one thing to briefly mention before we proceed on this one. So just to give you an idea how that works. So people go through this flow, have this project design, then they have something called a Carvel harness, which is an open, let's call it, boilerplate for the design, also as open source available from eFabless, which gives you some interfaces like power supply, a small little CPU, but also the inputs and outputs and some analyzing tooling. And then this is all being put together to essentially be able to produce these 40 and something designs. Okay, now coming back to my major point, 40 designs is not enough. So on the very first tape out, Matthew Wen actually came up already with an idea to even cut it down even more. So he actually took this project design you just saw on the left and said, there's enough space actually for 16 additional designs if you just make the design smaller. So here you have a 300 square micrometer, which is still a lot, and I will also mention in a moment what you can do with that actually. Here you already see the possibilities now of open source. So eFabless released this boilerplate Carvel harness, and Matthew used that and changed it in a way that it now supports not just one design, but in this case 16. And this is essentially then how it looks like. So essentially he can now go to 16 people and they can all put something in. So now you could actually come already to a point where you have like theoretically 16 times 40 designs. So something like 640 designs could now theoretically be put into one shuttle. So moving on, if you can put 16 on it, you can even put more on it, of course, if you make it even smaller. And this is actually because the interest became higher and higher over the last 1 year. So now there is an initiative called Tiny Tape Out, where they actually put 249 designs in one of these user spaces. Now we go down to something like 150 micrometers times 170. That looks in the end like this. Of course, the area is much smaller, but you can still do something amazing. I will also mention in a moment what that actually means. Very interesting, and this is actually one of the areas where you can already today participate. So this is cost-wise really insignificant. So I do not want to go into much detail here, but just to give you a general idea what we are talking here about. So these multi-project wafers, as I mentioned before, were already available. Now the key point is that they are all open, so we can talk about it. And this company called eFabless has this Chip Ignite program, which costs something like 10,000 US dollar, where you have essentially this 10 square millimeter for one design. This is what Google essentially sponsored. But you can also now just buy it. So the main question is here actually, what if Google at one point stops paying for all of that one? Obviously, we still want to proceed. So 10,000 US dollar is achievable, but is still quite expensive. So it's quite an ambitious hobby you have to invest that. So there we come to this point where Matthew went in and set up this CO2 ASIC course, where he now then accumulates like 16 designs. So you can make a course with him. He teaches you how to design these chips, and then you have a certain area. And do not look too much on the exact number for the price, but it's a very naive estimation that, okay, you can now just provide 16 designs, but of course you have some additional cost. But we are at a ball figure, an order of magnitude cheaper now with this kind of setup. And then last but not least, we have these tiny tape outs. And again, the real cost at the moment is like 100, 125 US dollar. So just take it as a ballpark figure that, again, we can cut off an order of magnitude. So price-wise, nothing stands between you and taping out your own chip. Price-wise, this is not a question. So I think we have a very brief time to look at some interesting things. So with this multi-project wafer, so on 10 square millimeter, what you can do is, and what people have done, is like in RISC-V based Arduino. So that's not theoretically impossible. You can do it. You can, of course, do Bitcoin mining, obviously. And very interesting, you can even build very small one, though, FPGAs. And this is now becoming very interesting that you now can design an open FPGA, which also supports this place and routing based on open source software and bitstream generation, because in the past, all the proprietary FPGAs actually have also a proprietary bitstream. But now we essentially have an open FPGA, an open tool, an open bitstream, so we are really now in complete control. So for this 300 square millimeters, micrometers, what you can do are like RGB mixers and accelerators for encryption methods. Someone has implemented a Pong. And then maybe you think 150 times 170 micrometer. What can you do with that one? So I, for example, designed a very small CRC calculator, but you can also build like a guitar tuner, and there's also people who have done a temperature sensor and even a PDP CPU. So then last but not least, price-wise, I think I have hopefully already convinced you that this is no, even for a non-ambitious hobby, you can do that. Now, another thing is, of course, knowledge. And with all this open source tooling, also the amount of open knowledge is increasing. So two honorable mentions I want to mention here is a web-based tooling from UE, who has essentially built a tool where you can, on a substrate level, draw, like with a paint program, your semiconductor design, and then even simulate it. And technically, that's quite interesting. So he, for example, uses Spice, compiled to WebAssembly, and lets it run in a browser. So you can really do also then simulation on top of the designs you are drawing there. Very interesting. But in general, you probably do not want to make anything complex now with that. And for that, there is another tooling. So if you might be afraid about Verilog or VHDL or HDL in general, like, for example, me, I'm still not really used to this kind of thinking. There are tools like VOCV, which were originally designed for circuit designs. So you can, for example, put an Arduino in, put an LED on, but it turns out that you can also use that to design your ASIC. So it doesn't look on the picture like that, but there is a REST API where you then can call your project's properties and then generate out of this design HDL. And comes now also, again, a lot of open source innovation. So Matthew from the Tiny Tapeout actually used this kind of tool in his GitHub actions. So you can actually just draw your design, make a pull request to your project, then the GitHub action from Matthew calls the REST API to get the HDL, and then automatically exits the whole flow, which was quite long, as you remember. So you do not really need to understand all the stuff in the middle. You really can, if your design is properly synthesizable, perform this flow very simply and very quickly. Good. So now maybe coming back to the thought-provoking questions. So again, do you have basic knowledge how an ASIC is made? So I hope you can at least say, I guess somehow, I mean, it's a complicated thing. I cannot give you any money back if you still do not know at least the basics. I hope at least you have a general idea what does it take. And if you just take with you that it's a complicated process, I think that's already good enough. Furthermore, do you think an open source ASIC is possible? So it looks like it. So to be quite clear, the stuff is not very mature yet. It works. We can do it. But yes, now we can do that today, and we have done it, as I've shown you. And then last but not least, do you dare to design your own ASIC? And I would say that this should be an enthusiastic. Sure, of course you can do it. You do not even need to really understand the whole process. And this is actually an important point now, that you do not need, at the moment, any money. In the future, just a little bit. You do not need a lot of time because the process is quite optimized. The only thing you need is motivation. So if you have that, you for sure can do that today. So with that said, I would be at the end. So if you cannot tell, I'm personally very enthusiastic about open source semiconductors. And you should be too, because you cannot only do it today, and this is something you couldn't just do like 2 or 3 years ago. This is something you can do now, which seemed impossible 3 years ago. But the whole infrastructure is not yet completely mature. It can be done, but if you actually use it, you will notice one or the other thing actually needs improvement. And this is actually now a great time for you then to look at this, contribute, and then essentially join this final frontier of open source. And with that, I would be at the end of my talk, and maybe we even have some time for questions.
First question, how many designs did you already do using that approach?
So I only made one, which was actually put into one of the tape-outs, but privately I made maybe a handful. But I personally did just one. What needs to be mentioned again, this kind of tape-out comes from this Matthew Wen I mentioned. Also a big shout out to him, who helped a lot in understanding a lot of these things. And he as an individual probably made the most designs, which are probably in the dozens now.
And then you have a minimum amount of chips you have to order, or?
Yes, so I made a list briefly. I think it depends on the packaging. For the multi-project wafer, for different packaging, you have either 100 or 300. I think this one was produced as a piece of 100. And then, of course, depending how many people participate, you are cutting down the amount of pieces the individual person gets. So just as an example for this tiny tape-out I mentioned, the cost would be something like $25 to get your design in, and then another 100 to get your chip with a PCB around it to really make something meaningful with it.
Okay.
Yeah.
Cool.
I actually made some ASICs in my former life at Siemens, and one of the big issues was test patterns, because you need these to verify that the process of manufacturing your device was okay. And we did some big length in fault simulating and all that to verify that our test patterns are good enough to find defects on the real manufactured chip. How do you do that in your open source environment? What tooling do you have for that?
Yes, a very good question. So that is done with some of the tooling I mentioned, but to be very clear, the first tape out actually didn't fully work. So it's also kind of open source mentality that let's try often and fail fast. Actually from Tim Ansel, the guy from Google who sponsored and managed a lot of the things, his intention is actually that if a tape out works 100%, then it wasn't good enough in terms of trying out fancy enough things. So the intention is really to do something where we do not yet know if it works. But it's there's tooling and there's a lot of cooperation with eFabless and Skywater to perform a lot of testing before. But we are currently at a stage where we also still have some other tooling, also including from Mentor, to do some additional checks, and some of the things are actually being noticed then at this point. So at the moment it's really in a learning phase. So the MPW shutter, so this first thing actually had some production issues, not from the manufacturer, but really from the design, as there were some things not properly integrated and tested. But we get from Skywater a model of their, for example, standard cells and how their system behaves, and we can simulate that before we do the tape outs. So the basis is there, but it needs to be improved quite a lot still.
So what do you consider now the limiting factors to scale this? Maybe both in a number of users being able to use that, but also regarding the density and then the manufacturing size to shrink it down to get even more complex things. I guess the testing topic is actually something I forgot, but it's a very important thing. Are there other limitation factors? Is this something, also commercially, what are the blockers or the unblockers to make this a success story possibly?
Yeah. So I think the biggest factor at the moment which limits us is Skywater. So it turns out that I mean, that seemed in the beginning like a small little hobby project for them, but now they actually received outside of the OpenMPW shuttle also a lot of requests on this one, and obviously there are like big customers behind that one. So now from an open source perspective, we have a little bit an issue that there's only so many shuttles we actually get from them. So really the fabrication seems to be the limiting point. I hope that with Global Foundry now also having this open PDK, this will release a little bit, relax a little bit. I actually do not believe that, and I actually expect this question to come later, that we actually have rather old nodes, so like the nodes we have like 20 years old. I actually do not really believe that this is a limiting factor at the moment. We could still do amazing things on these old nodes, and they are very mature. So I think production-wise, I do not think that there's any limitation. There's certainly limitations about the production and being taken serious also by maybe some people who usually do that in a different way. So, and because we actually also want that people who do it professionally come into the space and then bring their expertise with us and with them to improve the tooling. Because I guess we miss a lot of things which are very clear in the industry.
So then I would say, hey, thanks a lot, Daniel, for providing us